turn on. Yeah. How are we doing on time? Yes, we're doing good. Yeah, do you say no that time? Okay, it's 8:45 on a Wednesday, May 26. It's lecture 11 on multibody dynamics. I think if I look at the schedule, it's the 4th last lecture, right? And today's topic is the continuation of last week. Rotation matrices, Euler angles, and maybe a little bit about Euler parameters, but I'm only going to point that out where it is in the book, and that's then for you to read by yourself. Okay, since we continue with last week's stuff, let me check if everything is running. Yeah, looks good. Since we continue with last week's steps, let's do a small recap of the notes where we ended with last week. So the major new thing I introduced there were Euler angles, right? The 3 Euler angles. And I like to emphasize there that it was like a recipe. It's like baking a cake. There is an order in it. And the recipe was like this. So okay. So you first align your body fixed axis with your inertial axis, and then there's these 3 steps. First you rotate about the z-axis, then about the rotated x-axis, and then about the rotated z-axis. And then you can make a drawing, and that the drawing doesn't make much sense. It's ugly because everything is centered around this, and you have no clue, because yeah, we want to show 3D and 2D. It's always a projection, so that makes it difficult. So then what we do, we rely on these cans in series. So these are these hinges, these joints, revolute joints, where you have this relative rotation about an axis. And we just put these 3, we first divide and conquer. We first do the z-axis rotation, then we only look at the x-axis rotation, and then again the z. And then we concatenate those 3 rotations, and then we see that the transformation is then this series of matrices from the body fixed coordinates to the inertial coordinates. And as we see, it's a matrix multiplication, and I try to stress out that the order of the multiplication is in the matrices. It's important. If you have 2 matrices, A and B, they're not equal to B. If you reverse the order to B times A. In vectors, you don't have this. The order doesn't matter in the multiplication, or in addition and subtraction. But we look at multiplication now. So if we have two vectors and we take the dot product, then A dot B equals B dot A. So there's this, I don't know how it's called in English, associative, yeah, I think it's the associative thing. And then also with scalars it's the same. A times B is B times A. 2 times 5 is 5 times 2. But with matrices it's not. And why is that important? Well, in this recipe, you should not change the order. And therefore I always say it's like baking a cake, because for baking a cake you just do not light the oven and wait 20 minutes, and then after that you throw in all the ingredients, right? Or you do throw in everything, put it in the oven, and after taking it out of the oven you start mixing. That doesn't work either. So there's a definite order in that. Okay, to emphasize that, I want to do a small demonstration. And that small demonstration works like this. I have two rotations, and for now, for Pete's sake, let's assume I write these rotations as vectors. We will see in a minute that they are not. But so rotation number one is that I have a rotation of 90 degrees about the x-axis, and about the y and the z I have 0 rotations. And rotation number two is a 90 degrees about the y-axis, and then 0 about z and x. Now I have to pick some Euler angle system, and as we have seen how many different are there, there's 3 times 2 times 1 or something like that, like 2 times 2 times 2, 2 times 4 is well, something like that. Did you figure it out already, how many different Euler angle combinations there are? It's a nice question, actually. Okay, for now I want to do the yaw pitch roll, I guess. No, let's do another one. What did I do here? So, and that's the fun actually of these cans in series. You just draw the cans and then you have the order. So first, this is apparently the inertial system. I have the z-axis up, and of course then I have the x-axis forward, and of course then, since we all work with right-handed ones, meaning if you rotate the x to y and you take a positive corkscrew, then you go up, so then the y is here. Then in our set of type of Euler angles, we take one we call alpha around the x-axis, beta around the y-axis, and then, well, a smart mouse can guess it, right? Gamma around the z-axis, and then here we end up with our body fixed coordinate system. This is a small z, this is a small, and this is small y. Okay, so this is the order, right, of a rotation initially. Like in the recipe, align these things. But now we're gonna do two things. So first, we're gonna do rotation 1, and then we're gonna add rotation 2. And then we're also gonna look at the other way around. We're gonna first start rotation 1 and then do first rotation 2 and then rotation 1 and then. Now usually I do this with you as subjects in class. I say stand up, rotate about your x-axis, rotate about your y-axis. Unfortunately, we cannot do that. Everybody sits at home behind their computer, and so that doesn't work. So what we do then is we take a book which has a clear front and back and sides, and so which are distinguished. I drew a coordinate system on that, so the x is in this direction, the y is in this direction, and the z is up, right? So you could say, what did I think? Yeah, so like this is the forward direction, right? Like this is the forward direction, and then this is the sidewards, and then this is up. Okay, x, y, z. Now what am I going to do? I'm going to rotate. And I have these two rotations, R1 and R2. So first I'm going to do a very simple Euler angle where there's only one rotation. That's about the x-axis, right? 90 degrees. So that's super simple. And then on top of that I use that same set of Euler angles and I do about the y-axis. Now the y-axis, of course, in this case, is of course this one. So 90 degrees, I end up with the book like this, right? Okay, so can you all remember that? Then the next step is I do R2, first the y-axis and then the x-axis. So again, so first the y-axis, 90 degrees, and then the x-axis. Was it the x? Yeah, and then I end up with something like this, right? And then you would say, no, that's wrong. So these two orientations are not identical. And then you say, yeah, but you should have used the body fixed, the rotated axis. Well, if you do that, you still end up with two different orientations, right? So in one orientation, I think, how did we end up? Let me do that again for the notes. So I started with the x, right, 90 degrees. And then I do about the y-axis. And the y-axis was here, so that's plus 90. Oh yeah, I get the back of the book. I did it the wrong way around. So I ended up with this, the book. So this is the book. And on the back we see here, so this is the dark side, right? And here's the spine. Okay, and the other way around was R2, so a line again, right? X. R2 was about the y-axis, 90 degrees, so book like this. And then about the x-axis, right, 90 degrees, so we end up like this. So then the book is orientated like this. What do I see? That's pretty hard to draw. So I see the front of the book and the bike is here, right? And here's the... Okay, yeah, and here are the pages. That's good. Okay, it should be a bike, right? Okie dokie. And this was the back, right? Where's the bike then? Oh yeah, you cannot see, the bike is on the other side. Now we end up like this, right? So the bike was somewhere here. Here's the bike. Okay, though. Anyway, my point made. You get two different orientations. So the order matters. That's what we always say. R1 plus R2. If we call this these rotations, is not equal to R1. The order of rotation is important. Okay. Now let's address this other point where I was saying, well, let's pick one. How many different Euler angle systems are there? How many different Euler angle systems are there? Well, as you see in this picture, this is another one which I initially showed. I think what I started with the ZXZ. Oh yeah, no vectors. Euler angles. No vectors. Okay, though. So how many different types are there? Well, let's just start by trying. So okay, we have our coordinate system here. Let's say this is the inertial one, right? And then Well, the first one, the first thing you can choose, you can either do about x, y, or about, so let's do capitals, right, about x, y, or z. So you have like these choices. Then from that, if you have chosen, for instance, let's look at this one. We take the x, right? So the first hinge is about this. Now the second one, how many choices do you have? Well, you shouldn't do x again, because then you have like 2 in series, and then it's just the sum of those 2 rotations, right? That doesn't really make sense. So if the second one should be perpendicular to this one, and you have 2 directions here. So I mean you have 2 choices here. So you could say I do y or z. Now, and of course you understand. Let's take one, right? Let's say suppose we did the y one, and again now you have 2 choices, right? So if I end up here, I can do x. Well, y doesn't work, and z. So I can do x and z. And here, what can I do? When I do the z, I can do x and y. So what do we see? So we start with these 3, and then we have 2, and then 2. So it's 3 times 2 times 2, right? Which makes 12. So we have 12 unique ways of defining Euler angles. And they live, so 12 ways, I could say, for the Euler angles. And they have all different names. So some are called with the spin notation and whatever, I always forget. That was the initial one. That's the famous one, the ZXC. What is it called? Notation. No, that's not correct. Well, anyway, look it up. And then the other one is a yaw pitch roll. That's a one which we use a lot. So yaw pitch roll is mainly Z YX, if I'm right, or maybe ZXY. And then they also have all kind of crazy names like Cardan angles. If I remember well, Cardan angles. I don't know what the order is by head. And the other one are Bryant angles. Apparently Mr. Bryant has sort of that order. Anyway, there's a whole plethora. Well, not a whole plethora, 12, right? Okay. Of course, there's also different ways to do that. And that is when you do not put them perpendicular to this one. And then you have like an infinite number of choices, because you can do 31 degrees or 32 or 30.141592 degrees or radians or whatever. So then you have an infinite set, but I don't think it's a smart move to do that. Sometimes it's done. Like think of a bicycle where we have the head angle which is under 72 degrees related to the roll of the bike. But if you want to use a set of descriptive, simple way of describing a rotation in space, then it makes sense to use perpendicular axis. In the same way, like we use perpendicular axis when you do Cartesian coordinates. I mean, you could do right angles at the, but yeah, makes everything more complicated. Okie dokie. So that's where we left off. The next step is, of course, velocities. Until now, we looked at position, describing position, and the next step is, of course, velocities, and after that, accelerations. So for velocities, what do? Well, again, we draw our potato, right? We have our inertial system here. X. Oh, go back. That's good. I'm gonna draw. Shift. X, Y, and Z. And then here's some body fixed coordinate system, right? I should say triad, because a coordinate system is a triad with an origin. Okay, z, y, and x. And to really, because my handwriting is not that clear, I put a prime there to really distinguish between the body fixed coordinates and the inertial fixed. Then we have this point P, right? And remember we had this position x, P relative to C, the center of mass. Then we had this position being xp, and then we had this position xc. And the famous way of how do we get to point P? That is xp is xc plus xp relative to C. And of course, everything these are just vectors. In the end, in MATLAB or any other thing, or in MATLAB or what is the other, Python, or any other thing, we always calculate with algebraic components. Algebraic components. Or in other words, we have to pick a coordinate system. So you could either say, well, I do everything in my inertial coordinate system, or you could say, no, I do everything in my body fixed coordinate system. Now there is one big advantage, of course, for this coordinate fixed coordinate system, because this body fixed, because in a rigid body, this is constant. This relative distance, this one is a constant quantity there. So that is useful. However, we always want to express our position usually in an inertial system, because that is where all the laws of Newton are defined. So therefore we need some relation, well, let's say a relation between these two. And how does that then work? Well, in the end go back to here. So in the end you want to know the position in space in our inertial system, the algebraic components, and that is this guy, and that's usually what we use for calculation, x, y, z of the center of mass moving in this coordinate system. And then the other one we're going to express usually in their body fixed, because they are constant, that's then a constant vector. But then we need in front of that this rotation matrix. And that was a topic, of course, of last week. How do we get that? And it's the multiplication of these three simple rotations, and the order is important, and blah, 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 blah. Okay, we know that now for now. Then velocities. How do we get velocities? Well, that's sort of simple, right? It's the difference is a dot. The difference is a dot. So how does that work? Well, we just say x dot of P is x dot of C plus x dot of P relative to C. Now some of you would say, yeah, but this doesn't change. Yeah, well, the thing in the body fixed coordinate doesn't change, but since the body rotates, of course, it has, due to rotation, it has some velocity due to the rotational speeds. Or, if we now look at in more detail to this one, this was the general vector expression. Let's take the algebraic components, and the differentiation can be done in the same way on the algebraic components. So we get x dot of P expressed in the inertial system, the x dot of C expressed in this one, plus, and then we should do the chain rule, right? R dot Pn xpc P plus R Pn rotation matrix times the time derivative P relative to C in the body fixed frame. But of course this guy is 0, because the thing is constant. Within the body it doesn't change. So then we are left with this part. So this is the expression for the velocities. Now this we talked about a lot, so that's not so important. What I want to talk about today is this part. So the velocities of this relative thing, you could say, well, I want to talk today about x dot P relative to C expressed in the inertial system, which is the difference between this one, and that's this R dot P times this x P PC in the body system. So that's what we're going to talk about. So then we can find out what are these velocities due to the change in the orientation. Now notice that that we use two different frames here. So two different triads. Two different triads or coordinate systems. And it's sort of more handy to express everything in either say I want to have everything, I want to think my vectors are in inertial or my vectors are in a body fixed frame. So yeah, since we want to do Newton actually in our inertial frame, I like to express everything in this inertial frame, right? Meaning I need an expression for this in the inertial frame, so I'm going to write x dot p of c in the inertial frame is, well, this doesn't change, this is just the time derivative of this matrix. And now I want to express this one in the inertial frame, meaning I need the vector in the inertial frame, but here it has to be in the body fix, right? So I have to use a transformation matrix, and that goes like this. Then if we collect the terms, we can say, okay, I have this guy, and I have this guy, and then I have this guy. So now I have my expression of my velocity of point P relative to C. Yeah, and I have these two matrices. Well, of course, they what is the time derivative of the other? And you would say, well, no, the B is here on top and the N is down, and here the B is down and the N is on top. But we can fix that easily, because remember that. So for now, let's do a shorthand notation. Let's call this guy the matrix R. Right? That's shorthand because I don't want to write so much. So if we go from the body fix to the inertial, we call that the rotation matrix R. Then of course this will be R dot, so we get x dot in N, P over C is this R dot. But here we have the other matrix, we have like the inverse, but we know the inverse is transpose, right? So we know, oh, it's R transpose times x P of C. And for now, let's now, since everything is in N, drop the N. I mean, that's super ugly, of course, but it makes our writing a lot easier. So then we say, okay, so the velocity is R dot R transpose times that vector. Now, the big question is, of course, what is this? What is this guy? R dot times R transpose. It looks like a very complex thing, but remember, we had all these, that R needs to be, what does it need to be? Orthogonal. And I always like to say orthonormal, because what we discovered from the rotation matrix, that the inverse is equal to the transpose, or in other words, we discovered that R times R transpose should be the identity, right? Now, this looks almost like that. Almost. Watch what happens. To get this, what do? We need to differentiate, right? So let's do that. So we get, we do differentiate with respect to time. We get R dot R transpose. That's the guy we want. Oh, but we get more. We get R equals, zeros, because the time derivative of I is a constant. Now this looks a lot like this actually. Now watch what happens if I do this, and if I take the transpose of this guy, I get R dot R transpose is 0, right? If you transpose this guy, you get this. So I have two matrices, so let's call R dot R transpose W. For Pete's sake now. Now, if we use this, then what do we get? Then the conclusion is W plus W transpose should be 0. All zeros. And remember, these zeros are 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. 6 zeros. Well, which matrix, when you add it with a transpose, gets all these zeros? So we have to have a matrix, and it has 9 entries, and the 9 entries, if you take the transpose and you add them up, then, well, it means first of all that, of course, at the diagonal there must be zeros, because the diagonal doesn't change when you do the transpose. Ergo A plus A should be 0. If you call this entry A, then ergo A is 0. B plus B is 0. C plus C. So these should be 0. Otherwise, this doesn't work. And then again, every term you find here should have a negative here. So we only have like 3 terms which we can fill in. So you could say A, B, C, right? A, B, C, and then minus A, minus B, minus C. Well, that's good. This would work, only 3 parameters, but I'm going to do a little bit different ABCs for now. So yes, we have only 3 numbers, but I'm going to write them in a cranky way. I'm going to write here an A, I'm going to write a B here, and I'm going to write a C here. And you would say, why does he do that? Trust me, I'm a doctor, it will work. Minus B, minus C, minus A. Then, of course, W transpose is again this 0, that's super easy. And then you just flip the whole thing, right? C minus B, A, minus C, B, minus A. And of course you can check, if you add these two up, of course the answer is all zeros. So that works. So this is a nice way of defining this omega. Now why so strange with the A, B, C, right? Well, actually, if we now take this matrix W and we multiply it with a vector, so we do this 0, 0, 0, right? And then we get A, B, C, and here minus A, here minus B, and here the minus C, and then a vector X, Y, Z. What is the answer? Okay, the answer is minus C times Y plus B times Z. Okay. C times X minus A times Z. Okay. Minus B times X plus A times Y. Actually, this looks a little bit like cross product, right? I mean, there's no X and there's no A here. So it looks a little bit like this, like A, B, C, cross product X, Y, Z. Check it out. So the first is this times this, B times C minus C times Y. Yeah, that's correct. Aha! So this way of writing this strange asymmetric matrix times a vector, in this way, actually is a way of writing the cross product, and we know the cross product. Now if we now define our matrix W as such, and we call this 0, 0, 0, we call this omega 1, omega 2, omega 3, and then here these guys. Then we could say that this W times the vector x is like, and then we have a vector apparently omega, omega 1, omega 2, omega 3, a vector omega cross product x. And that's exactly what we remember from our simple velocity analysis in the past, in the 2D case, or in our simple dynamics. Now usually we write then not W here, but we write this omega with a tilde, and that means you use this vector omega and you write it as this matrix. So that's what we call the tilde notation. Omega 2, omega 3, minus omega 1, minus omega 2, minus omega 3. Tilde notation. So that's to go from a vector to this Q-symmetric matrix. From a vector, you go from the vector omega to this Q-symmetric matrix omega tilde. That's the way. That's what we use this tilde for. Because the symbols from this guy comes in this matrix, and we don't put an underscore here because it's a matrix, right? It's not a vector. Okay, that's a nice way of writing that. Now back to where we started in the beginning, right? We wrote x dot equals, what was it? R dot R transpose times x. And now we know, if we now define R dot R transpose as this omega tilde, with these omega vector, omega 1, omega 2, omega 3, only 3 parameters, then we can say, oh, x dot is omega cross x, or omega tilde matrix times x. So here we now have a nice way of defining our angular velocities. But the big question remains, of course, how do we get this omega, and then you should say the vector, from this R dot R transpose? Because we have R is in, well, in the 3 angles. What shall we say? I had the 3 Euler angles, phi, theta, psi, right? Euler angles. So the variables here are 3 Euler angles, and if you then differentiate this with respect to time, what do you get? Well, then R dot is by definition dr d phi, oh man, my brain, phi dot plus all these partial derivatives, d theta dot plus dr d psi dot. So yeah, it looks like, it smells like we have these 3 velocities, but phi dot, theta dot and psi dot are not directly our omegas. So we have to find a way to find the relation between these time derivative of the Euler angles and these angular speeds. So, well, the definition is clearly here. So what we do is we just take the definition. Where is the definition here? So we say, oh, well, apparently R dot, oh, bad handwriting, R dot R transpose, was defined as this omega matrix, right? So what I have to do is I have to take this expression and then multiply everything with R transpose. So I get the dr d phi R transpose times phi dot plus the dr d theta times r transpose times theta dot plus the dr d psi r transpose times psi dot equals, and maybe we write out the matrix, right, to see what are we actually doing. So that's this 0, 0, 0, omega 1, omega 2, omega 3, minus omega 3, minus omega 1, minus omega 2. Now here we have to reflect a little bit. So we now found a relation between omega and phi dot, theta dot, and psi dot, right? And of course we also see and they depend on the angles themselves, phi, theta, and psi, right? Because these matrices, they all depend on the angles. But what we also see, it's linear. Eh? It's linear in omega versus what is it? Phi dot, theta dot, psi dot. There's a linear relationship between them, and meaning that in the end, we should be able to write it like this. In the end, we should be able to write. Well, since it's a linear relationship, and I have here a matrix, and I have everything is linear in phi dot, theta dot, psi dot, and here also, then I could finally, and I don't know how yet, but we should be able to write it something like this, right? And this is a whole lot of shebang before these time derivatives of the angle. So phi dot, theta dot, psi dot. Now, and then the outcome is here omega 1, omega 2, omega 3. So 3 equations, the first for omega 1, the second for omega 2, and the third for omega 3. Now note, by the way, if you look at this equation, you see that we do not have 6 equations like I write them down here, but we have 9 equations. So we do a little bit too much here. So first of all, we calculate a lot of zeros, because if we do our work right, then really these diagonal terms which we derive here should all 3 be 0. Well, that's a nice check on your work. And the other thing is, if we calculate this number from this, then that should be the negative of this one. So we do like double work. Now, I know students do not like double work, and professors even more do not like double work, although it's a nice way to check. So is there another way to do it? First of all, this is the route to go. So if you don't know, you just put it in MATLAB, symbolic expression, shebang, turn the machine, and you get your numbers. But maybe there's another way. Maybe you have a physical interpretation. Now, those are dangerous bands, again, physical interpretation, but let's still try and do it. So maybe easier is a physical interpretation. And how does that work? Well, let's start again with the cans in series. And what did we do? We did the original Euler angles, right? So again, original Euler angles, I have to give the axis names. So I usually Z up, although aircraft people tend to have Z down. So, meaning if your Z is positive, you crashed, right? Crazy guys, aeronautical engineers. Anyway, yeah, so let's take this set. So we start about the Z-axis, which we call phi, Then we do the theta axis, so this guy, which you call theta, that's the x-axis, right? And then again the z for this guy, and we call that psi. Okay, let's put the coordinate system there. This was inertial, this was body, x, y, and z. For now primes, although I had to clearly, because then in the hand triangle you don't see it so clear. And I usually write this to say, well, this is, we start from the inertial frame. Let's get rid of all these messages. Nope. Okay, now yeah, an easier way. Well, first of all, from a picture it's maybe hard, but if we talk cans in series, we know absolutely that the rotation, like for instance, if we take if we want to look at phi dot, then we know that happens here. So phi dot is about that, and it's really, we know what the axis is when we have a cans in series or this thing. So we know, if we have to draw a vector for that, we know that there is a vector and that the rotation is about this. There's a vector omega, and I'm not going to say in which coordinate system, and we call that omega phi, and it's the rotational speed in this case. I'm not going to say that, because I keep it just as a vector, because as a vector it's good. If this is the direction, then this is the omega theta about this axis. Likewise, the second one, I can write a vector here, right? And I call that omega theta. Why not? It's a vector, the rotation is about the thing. Maybe the vector changes, but that doesn't matter. How are we doing on time-wise? I need 15 minutes more. So I'm going to stop the lecture at 9:45. Do we all agree? Yeah, okay. I'm happy. Okay, then the last one, of course, rotation about this guy is the omega about this axis, omega psi. Now for the omegas, they are vectors. These are clearly vectors. I haven't said in what coordinate system yet, but for these vectors I can say, well, the omega is now the vector sum of these, because they are vectors, right? So it is omega phi plus omega theta plus omega psi. Now I wanted to write components here, but then I have to decide a coordinate system. But actually that's sort of easy, because I can pick a coordinate system for this. I know, and that's super easy. Easy is omega omega phi in, well, in the inertial frame, right? That's easy to say, because then it's about the z-axis. So then we get 0, 0, phi dot, right? Another one which is very easy is the last one, which is this omega psi, because that is easily expressed in the body fixed coordinate system, and that is 0, 0, psi dot. By the way, notice again that now the psi dot and the phi dot are in the same place. So if they were like vectors, then the Euler angles, that wouldn't work. I mean, then they would be in a different place. But they're not vectors, right? Euler angles are not vectors. Never, ever, Mr. Faulty. I know nothing, right? Now the intermediate one, so that is what is the omega theta. Well, that's a tricky one. For that one we have to introduce a triad, and that's the triad which is attached here, right? We haven't given it any name yet. So attached to in this coordinate system is a triad, which we call, how did I call it, F. So that triad F, this guy, is attached after hinge number 2, right? And I know within that f coordinate system, it's simply about the x-axis, so it's theta dot 0, 0. And now the trick is very simple, because now we have to combine these components and write everything into one coordinate system, right? But we can do that because that's what we learned in our previous lecture. How can we do transformations from one coordinate system to the other? Okay, yeah, so let's say we want to express our omegas in our inertial frame for now. So in our inertial frame is, well, we can easily start with this guy, right, in the inertial frame, because we have that guy in our inertial frame already. Then the next one is the omega theta. Now we have to do something, because that is in the F frame, and I need a rotation matrix which goes from the F frame to the inertial frame. And again I have an omega, what was that, the last one, the psi, and that's in the body fixed frame, and I need a rotation matrix from the body fixed frame to the inertial frame. Then the next step is, of course, filling in these rotation matrices. Yeah, and if you do that correctly, and then I again think in these different separate rotation matrices, and I write vectors immediately, right? So this one is the same already, right? I don't have to have any transformations. So what was it? Phi dot. Then this rotation matrix, so from F to N. Well, F to N. So F to N, the only thing which plays a role in this case is of course this rotation phi. And you could say, well, the other rotation also plays a role. That's a rotation about this theta axis, but that doesn't matter, because the theta axis doesn't change when you rotate about theta. So we could just easily take the rotation about only about this axis. Yeah. But yeah, okay. So the only rotation which plays a role here now is this r phi. Yeah, but that's not very nice actually. Let me add this guy. To go from this F system to here, we first have to do this transformation and then this transformation, right? So we have this order. Well, I'll get back to that in a sec. Theta dot 0, 0. And then the last one, that was this vector 0, 0 psi dot. Yeah. And then we have three rotations, of course. The last one being this r phi, r theta, and then we have the r psi. But by the way, this guy is not so important here, because the rotation matrix here is about the x-axis, and then the rest is all zero. So it doesn't play a role, but it doesn't matter for now. Okay, if we combine this, and that's a lot easier than the above expression here with all the dots and all the matrix multiplications, right? If we combine everything, where are we? 100%. Yeah. Then the following thing emerges: omega x, omega y, omega z in the inertial frame. As I promised to you, will be a matrix, because everything is linear. Now I need a proper order, because these are now vectors, but now I'm going to do something. I'm just going to order the three Euler angles as velocity vector. So phi dot, theta dot, psi dot, and not a vector, exclamation mark, blah blah blah, watch out, dangerous band, zzzt. Dangerous, you know this sign, dangerous band, dangerous band. Watch out, next corner. This is not a vector, but I just have to write them in an order, because it's a linear mapping, right? Not a vector. If I fail then in the numbers, and I just copy from my sheet here, it's a nice thing to do at home. Cosine phi, sine phi 0, sine phi, sine theta, minus cosine phi, sine theta, cosine theta. So we see a very simple linear mapping from the omegas to the time derivative of the Euler angles. Right. Now, usually the game is the other way around, because in your calculation, right, we start, how does it go? We have our Euler equation, sum of the torques, I omega dot plus, plus omega cross I omega. From this we get our omega dot, and then omega dot we integrate, and then we get our omega. But then the last step is, of course, from these omegas, I want to have my phi dot, theta dot, psi dot, which I then integrate, phi dot, theta, psi, theta dot, psi dot, with time, of course. And then I get my new angles. So that is the whole game we are playing. I want to know my new position, then I need my velocities expressed in my position. Oh, there's no dots there, stupid me. I need my new angles. How do I find the new angles? Because by integrating the speed of these angles, or speed, time derivative, let's say time derivative of these angles. How do I get the time derivative of these angles? Well, I get them from this transformation, right? Zit. And in this transformation, I put in the omegas and the current angles, and I get this time derivatives. So that is doable. I have to invert this matrix apparently. And how do I get my omegas? By integrating my angular accelerations. How do I get my angular accelerations? I solve them from my Euler equation. That's a long sentence to get the orientation. So that's how nature works. Sort of. Okay, this step, we still have to do an inverse here, right? Because given the current position and the angular velocities, what are its time derivatives? So we need the inverse. So let's do that. So we need phi dot, theta dot, psi dot equals, and then we have to do the inverse of this matrix, but the matrix is not so complex. So that should work, right? Omega. Omega y, omega z. This was an n, right? If I do the inverse, what do I get? Well, 1 over sine theta I get, and then I get sine psi. I probably make an error here, but it's correctly written in the book or on YouTube, or no, not YouTube, internet, Wikipedia, whatever. Although you should not trust Wikipedia, right? Sometimes there are errors there. Better do Eric Weinstein from Math, or from Mathematica. Anyway, so this is the inverse of that one, not so complex. However, I'm worried. I'm really worried when I look at this. And why do I'm worried? Well, because of this. This guy worries me. Because when sine theta is 0, we have a singularity. We cannot solve this. There's no solution. And when is sine theta 0? That's for theta is 0 plus or minus k pi. So already in the initial configuration, like this, we cannot solve that. Like, oh man, I did something stupid, right? So this is the initial configuration. This is body fixed. And this is inertial fixed. And then given these speeds, this speed, what is it, phi dot, this speed, theta dot, and this speed, psi dot, I cannot determine what omega is. And if you look closely at the picture, you will say, ah, I understand. Because this omega is in space. And all these omegas are in a plane. They are all in this flat plane, because these two axes are aligned. Meaning, you can, out of the plane omegas, you cannot describe. And it's easily seen when you write down the initial expression for omega x, omega y, omega z, without doing the inversion, filling in the numbers. So if we fill in the numbers and we fill all zeros, right, then the cosine is a number. Well, here everything with a sign becomes 0, so we get 1. This is all zeros, 1, 0, 1, right? Remember that? I can remember that. 0, 1, 0. This is all zeros, and this is 1, 0, 1. And this was phi dot, theta dot, psi dot. And this is exactly the problem. This is singular. Why? Well, look at this. We cannot describe any component in the y direction, which you can see already from the picture here. We cannot describe any omega in the y. There's all zeros. So in the x, in the z, in this plane, perfect. And even in the z is a combination of these two. Oh yeah, the combination of these two, right? So that's a singularity. And we call that Gimbal Lock. And I call that Gimbal Lock. Why? Because you can draw rotation as 3 gimbals. So one gimbal with axis, and then the other one is this, another gimbal, this guy, rotation about that. So there was the phi, and this was the theta, and then again, what do we need? About the z-axis. Then we need another gimbal. Oh, it doesn't matter. You can still draw another gimbal here. And then if one of these gimbals comes into the same plane, right, then it's sort of a lock. Now, there are solutions for that. You just reformulate the angles. And I want to finish it up now by a demo. And the demo is as follows. This is the demo, right? This is the demo. And I think with this demo, and on purpose I gave you this assignment, right? What was it? The bonus assignment on for homework 10, yeah, because they're out of sync, the numbers of lecture and homework. And what is this? Well, this is our inertial frame. Look at the label, inertial frame, with the x, the y, and the z-axis. And then I made, what did I make here? Oh yeah, I made yaw pitch roll, like in the assignment. So this is the yaw, right? And then we have a pitch, and then we have a roll. And that's all very nice. So from a vehicle point of view, like we're moving in this direction, and we can move to Amsterdam or to The Hague, or and then oh, we go over a bump with our car, and oh, we go around the corner and it's rolling, right? So bump and rolling, and then you see all your different I got a clashing, all your different orientations. All very nice. And you can play around with this and understand, okay, if I have some configuration, how do I get there? And you will see that there are like more ways to get into one configuration. But you can also show like this gimbal lock. So in this case, this is like a pure gimbal lock, right? Because axes are aligned, right? So, meaning, if there is like a rotational speed around this axis, or this axis doesn't, let's say this axis, the only way to do it is to break my system, right? This is out of elasticity. Then, due to elasticity, I can rotate. I should show Oh, only elasticity does it, right? And we're not talking about elasticity, we're talking about rigid bodies. So you cannot describe this rotational speed. You have to reformulate axis. Now, what you could do is you, for instance, make sure that they are not aligned. So make sure that they're not aligned. Say, I do this, and then, oh yeah, now I can describe a rotation. But note that that we now use a different set of Euler angles. Yeah, I can now describe this rotation, which I cannot now, but if I do a 90-degree change of coordinates here, I can do. But you don't want to do this 90 degrees of coordinates when you get near to the singular position, because then your variables are discontinuous, and all the numerical integration schemes, they build on that functions are continuous, and then you just make them discontinuous, and that's not smart, and then all your error estimates and so it doesn't work. Anyway, play around with your thing, break it if you need to. I take a 5-minute break, and then we go back to our Q&A. So Q&A in Zoom. When? Oh shit, time is running. 9. It's now already 9:50, so 9:55. Okay, I can leave that, yeah, and then we go to the Zoom. I stop this and we go to the Zoom. That's how it goes.